We continue our lesson about matrix theory. Uh, so we learned about how to do operations on matrices, and then last session, if you remember, we learned how to multiply two matrices if it is possible to multiply them. We solved a little bit of problems there, and let me now continue. Okay, the first thing that I have written it as an example, but if you want to work with matrices, it is extremely helpful to remember it, is that we want to show that if I have two triangular matrices of the same type and the same order, then if I multiply them, it definitely becomes another triangular matrix of the same type. So it means that if, I don't know, do you remember from the let me recall you a little bit from the very first session. So when I was discussing about different types of matrices, we introduced a matrix of this type where everything below the main diagonal is 0. I don't care about what is happening above the main diagonal. If I have a square matrix below the main diagonal, every entry is equal to 0. Then it is called upper triangular. Oh, and then if I have the other situation, if above the main diagonal everything is 0, it's called lower triangular. Okay? Now this example is asking us to prove that if I take two of these type of matrices, two matrices of this type of the same order, because if they are not of the same order, we cannot multiply them in the first place. But now, if they have the same order, I multiply them, it becomes again another triangular matrix of the same type. If you are multiplying upper triangular matrices, you get an upper triangular matrix at the end. And if you're multiplying lower triangular matrices, you will get a lower triangular matrices. And then this moreover is also interesting. Moreover, show that each entry on the main diagonal of the product matrix is the product of the corresponding entries of each one of them. I think it might be better, of course I want to prove it in the general case, but let us just work with 2 by 2 matrices to refresh your memory a little bit. So I would write with a different color, so this is not my solution. So let us concentrate on upper triangular matrices. So, for example, I have this situation A, B, 0, and C. So this is an upper triangular matrix, yes, because everything below the main diagonal is 0. And then I multiply it by another one. So let us say D, E, 0, F. So these are two main triangular matrices of the same type. And I want to multiply them, see what happens. So you remember, what's the multiplication? I decompose the left-hand side matrix into rows and the right-hand side matrix to columns, and then I take each row and multiply it by each column according to the rule that you know. Yes. So what should I do? So refreshing your memory, I take this one and multiply it here. How? I first multiply the first entries, it becomes a D. I multiply the second entries, it becomes 0. I add them, it becomes a D. And then now I go to the next one. I will take this row and multiply it by this column. I have to multiply A by E, I have to multiply B by F, and add them together. So this becomes AE plus BF. And then what I do here, I will take this row and multiply it by this column. 0 times D is 0, 0 times C is 0. So if I add them, it becomes 0. And then finally, you immediately can convince yourself that this becomes CF. So you see, now if I ask you what is the type of the product, you would say again, this is a lower triangular, sorry, this is an upper triangular matrix, because whatever below the main diagonal is 0. And you also see the pattern. So this moreover part is this part that you see. If I ask you what are the entries that appear here, you would say this is the first one. So it means that these are the products of the corresponding entries on the main diagonal. So A times D, C times F. So that is what we want to show in general. Okay, so Please interrupt me if you have any questions or there is something that you don't understand. Okay, so here let us concentrate again for upper triangular matrices. I recommend you to start solving it for the lower triangular matrices yourself later. So here, what is the main property? So let me first of all, if I have a lower triangle, upper triangular matrix, so it means that this is my main diagonal. Yes. So it means that everything here is 0. But do you remember I told you that whatever is inside here, its row number is greater than its column number. Yes. So these are the things we have already studied, so let me not spend some time on it again. So here the row number is greater than the column number whenever you are below the main diagonal. On the main diagonal, I and j are equal, and above that I index is less than j index. Okay, so it means that let me consider two matrices. So let A and B be upper triangular matrices of order n. You know that upper triangular matrices are square matrices, so I don't need to say how many rows, how many columns. I say just simply order n. It means n rows, n columns. Okay, we show that AB is also an upper triangular matrix. Yes. How should I show? I would say that let I don't know, be smaller. So let me write it in this way. So I would say let n be greater than or equal to I, greater than j, greater than or equal to 1. We show that the entry of a, b, I, j is equal to 0. So do you agree with me? If I can show this in general, I am done, because my claim is that the product matrix is supposed to be an upper triangular matrix. So it means that if I choose any entry of the product in which the row index is greater than the j index, this should be equal to 0. If I can show this, I am done. Okay? But how can I show that? I have a formula for the product ij. So do you remember? So AB ijth entry is equal to a sigma. I choose a counter for my sigma. It always starts with 1 and goes up to the number of columns of A, or equivalently the number of rows of B, but both of them are here n by n, so it goes up to n. And then I start with A and B. A should start with I index, ends with the counter of the sigma. B should start from K with K and ends at J. Okay, so how can I show that this is equal to 0? Because I is greater than j, so I can expand this sigma. I can say that, okay, I can go from 1, because I am supposed to consider all cases from 1 to n, but I can consider them case by case. So I will go up to j, I would say. K goes from 1 to j. Yes, do you agree? And then I would write from the same thing. And then there is one. Okay, let me go up to j minus 1. For j, I consider it individually. Let us see what happens. I don't know, might be I am making some trouble for myself. Then I will start from j plus 1 and go up to n. This is understandable, hopefully. I don't know if I am doing everything right, or should I go up to I or to j? I'm a little bit confused here. So let me see. It goes from, first of all, instead of going from 1 to up to n, okay, so this is not a good decomposition, I think. Okay, so let me not make things hard for you. So let me just expand the sigma. But you need to know that I is a number greater than j. So first, when I am running from 1 to n, I first reach to j, and then I will reach to I, and then I will continue. So it means that, let us consider these cases. So assume that this is your axis, and j is somewhere here, I is a little bit later. And I am running from 1, here this is 1, and here is n, yes? I want to run my sigma from 1 to n, so it means that I need to pass through these numbers. So let me just expand the sigma in this way. So I would start from 1, it becomes AI1, B1J, yes? And the next one is AI2, B2J. I will continue until I reach to the first index here, j. Okay, so then it means that I will have I and then j, b, j, j. The next one would be I don't know, j plus 1, b, j plus 1, and j. And then I continue until I reach to I. So this becomes I, b, I, j. And then I go to I plus 1. Yes, might be I am writing too much. And then I will continue, finally I hit the last one. It becomes what? I, n, b, and j. Okay, yeah. Is that understandable? So I'm just opening the sigma from 1 to n, but I am emphasizing to show these intermediate steps because I want to use them. Okay. But something about matrix A and matrix B I know. What is that? Matrix B is also an upper triangular matrix. So it means that if I have two indices, I don't know, L and K, and if L is greater than K, then it is 0. Why? Because the matrix A itself is an upper triangular matrix, it should have that property. The same is true for B, yes? Because B is also upper triangular matrix. So this is our assumption about matrices A and B. So let us see which one of them are gone. So what do you think about the first one? Is it 0 or not? Because I index here is bigger than 1, so this is 0, this is 0. Still this is 0 because still I is greater than j. So I don't know about b values, but I know that a sub I1, b, a sub I2 up to a sub ij, everything is 0, so everything so far is 0. Okay, but here what happens? Still I is greater than j plus 1 because they reach to the same value here. So everything here is also 0, but then here I have to be careful. AII, there is no guarantee that AII is 0, but let us see what happens after that. What happens after that? Here I plus 1 is first, j is second, but I itself is greater than j. Okay, everything after that is again 0. So what is left for me, if I understood it correctly, this is left, which is a little bit strange because it should be on the main diagonal. Okay, sorry, everything should be 0. Why you are not telling me? We want to prove that this is actually 0. So I am right. Everything was right. I myself was confused. So every term is now 0. Do you agree with me? Why this term is 0? because I is greater than 1. Again, why this is equal to 0? Because I is greater than 2. Up to this point, ij, it's also 0. I is greater than j. Yes, because this is assumed. So everything up to here is 0 because of a's. Even after that, I is greater than j plus 1, so I is a little bit further. So every term here is also 0 up to this point. Here, everything before this, it is ai minus 1 and I. Yes? No, sorry, it is ai and I minus 1. So this one, the previous terms, everything is 0. But when it comes here, there is no guarantee that ai is 0, but the good point is that now I is greater than j, bij is 0, bi plus 1 and j is also 0, and everything after that will be 0 because of b entries. So I was confused. I am so sorry for that. So the answer is 0, and we were supposed to show that this is 0. I don't know why I lost the logic there. Is that understandable? Yes? Now, if you want to, you can check it yourself. I spent quite a lot of time for this, for nothing. It's not a very hard problem. So now here, if I choose I and I the same, you just write the same thing, and then you will see that here there is only one term that might survive, and that is aii, bii. So that is exactly what we want to show. Okay, sorry, I think I confused you, but hopefully you now understand what is going on. Okay, so now the very important remark is this. It's very important to remember this fact. So if I have two diagonal matrices, it's extremely simple to multiply them. The diagonal matrices play a very important role in the matrix theory. So little by little, it's better to discover their properties. So one thing is that if I have two diagonal matrices, if you want to multiply them, it is extremely simple. Just multiply the corresponding entries. So why is that? Because a diagonal matrix is both upper triangular and lower triangular, so the product should remain both upper triangular and lower triangular. So definitely the product should be a diagonal, because if a matrix is both upper triangular and lower triangular, it is a diagonal matrix. And then here we showed that moreover, entries on the main diagonals are the product of the corresponding entries. So what does it mean if I want to show it to you? For example, if I have this matrix A 0 0 0 B 0 0 0 C, it's a diagonal matrix. If I multiply it by this, then what happens? It is not a new rule. I am using the same rule, but if I multiply this by that, the first one multiplied by the first one becomes AD. The other entries are 0 and 0, and if I add them, it becomes AD. It means that if I follow the same rule, there is only one rule to multiply, but at the end you will see that the result is this. It means that I am just multiplying the entries on the main diagonal together. Okay, and if I go, for example, if I go take this one and then multiply it by this, everything becomes 0. If I take this one multiplied by that, everything becomes 0. So when I add them, it is 0. And then when I go to the second row, the first one multiplied by the first one is 0, second one multiplied by the second one is 0. It is still 0. But when I come with this one and this one, the first time 0 is 0, the second one is BE, the third one is 0. When I add them, it becomes BE. So you see that exactly what's happening. I am exactly multiplying these entries corresponding. So that's a very important rule to remember about multiplying the diagonal matrices. Any questions? Okay, there are some notations that I want to introduce you here. If you have an m by n matrix with these entries, we use this symbol to denote the following 1 by n row matrix. So actually, if I ask you what is this, you would say that this is the ith row of my matrix A. Okay, so if I have a matrix, if you see this symbol, it means that take the ith row of that matrix. This would be this 1 by n matrix. And for this, if you see this symbol, it means that we are interested in the jth column of matrix A. Okay, so these are some pieces of notations that would be helpful. Any questions? Okay, so here there are some important rules. They are actually very important when it comes to matrix multiplication. We learned how to multiply matrices, but in the future you're supposed to prove a lot of theorems related to matrices, so it is better to see matrix multiplication from different points of view as well. So this is essentially the same thing. So if I ask you calculate the ijth entry, one entry from your matrix, do you remember? You decompose the left-hand side matrices to rows, and you decompose the right-hand side matrices. The right-hand side matrices to columns, and then you take each row and multiply it by each column. If you want to find the ijth entry, you take the ith row of the matrix sitting on the left, and you multiply it by the jth column. Okay. Another thing that is important, so let me just show this example to you here. So assume that everything that I show here, I will give you an example here. So assume that these two matrices are my matrices A and B. This is 2 by 2, this is 2 by 3. So A times B is defined because these are the same, and the answer would be a 2 by 3. So this we know. For example, if I ask you what is the 2/3 entry of the product, of course you can calculate the whole product. After it is done, you go and read this entry. But this is time consuming, especially if the order of these matrices are very big. And in practice, in more engineering problems, they are indeed very big. So if you are interested in only one single entry of the product, it's not efficient at all to find the whole product and go and find that entry. But we can use this idea that if I want to find only one entry, I go to my matrix on the left, yes, and take the second row. Any questions? Oh, oops. No problem. That's no problem. I'm just working here. So 2 and 3, it means that go to this matrix and take the second row, and go to matrix B, take this third column, and just multiply it. Okay, so to be able to appreciate this idea, let me multiply these two matrices completely. So A times B is equal to 1, 2, 3, 4, and then you have 5, 6, 7, 8, and 9. Okay, I just want to compare what I am saying is true. So let us just do this product in its entirety. So I will decompose these two rows and these two columns, and I will start multiplying them. Let me just do it quickly. It's 5 plus 16 is 21, 6 plus that is 24, and 7 plus 27, 15 plus 32 is 47, 18 plus 36, 54, and 21 plus 40 is 61. Yes, so this is the full product. Yes. Okay, now if I ask you what is the entry on the second row and third column, second row and third column, so you get 61. Okay, but I have done a lot of unnecessary calculations. But if I want to do it, this tells you that you can just go, if you want to calculate one entry, you can go and take the second row of the matrix on the left, it's here, and take this third column of the matrix sitting on the right, and just multiply them. Okay, but what is this multiplication? Let me just do it here. Only one multiplication is necessary. Is this multiplication doable? Yes, because it is 1 by 2, it is 2 by 1. So you see that the answer would be 1 by 1, and every 1 by 1 matrix is identified with its entry. So how should I do that? 3 times 21 is, so 3 times 7, 21, 4 times 10 is 40, and if I add them it becomes 61, and the answer is actually correct. So you see, it's simpler. Sometimes you are interested in one particular row. Yes, so for example, you are not interested in one entry, you are interested in the whole ith row of the product. If that is the case, you can choose the ith row of the left hand side but multiply it by the whole matrix B. So for example, if I ask you here, what is the second row of the product? You can of course read it here. It is this matrix, 47, 54, and 61. But I have done everything, and then I am just reading the second row. Again, I have done some unnecessary calculations. This theorem tells me that just take the second row of your matrix A, second row, and then multiply it by the whole matrix. You don't need to care about the first row at all. Okay, so if I want to do this, is it doable? This is 1 by 2, this is 2 by 3. Yes, it is doable. So the answer is 1 by 3 as expected, because that should be a row. Okay, if I want to do it, I have to multiply this by that, multiply this by that, multiply this by that. If you do this, you definitely get the one that is there. So it becomes 15 plus 32 is 47, and then 18 plus this is 54, and then 61. So you see that this is exactly the second. So I don't want to spend time on the second one, but I want to tell you about that. Now sometimes it is important you just concentrate on some particular column of the product. Again, you don't need to do it entirely. What you need to do, you can take the first matrix as a whole, yes, and just multiply it by the column of the second matrix that you are interested in. So you can just convince yourself about that. But a little bit non-trivial fact is this one. This type of decomposition is also very nice to know. This is the first time that columns of the matrix on the left becomes important and the rows of the matrix on the right becomes important. Most of the time this is the other way around. So this is called column row decomposition of the product. Okay, to understand what's going on here, let us again refer to our problem. Okay, so this is also nice. This is telling you another way for completely multiplying these two matrices. It tells you just take columns from the left and multiply them by the corresponding rows of the matrix sitting on the right. So you see, it's giving you again the whole pack. It's not just giving you one row or one column. This is another way to do multiplication. Okay, it's important theoretically to know this is doable. So let us understand what's going on. For example, if you tell me to multiply them, I have used to multiply it in the normal way that I described so far, but I want you to know there is also an alternative way to do that. What is the alternative way? The alternative way is to take the columns from the matrix on the left and take rows, this is the other way around, rows from the matrix on the right and multiply each column by its corresponding row. What does it mean? It means first column multiplied by first row as matrices, and then this one, the second column, multiplied by the second row again as matrices. Okay, so why is that true? Let us check this here. For example, assume that I want to calculate the right hand side here. I want to calculate the right hand side here. This is a 2 by 1 matrix. I want to confirm that this is correct. And this is a 1 by 3 matrix. Is it doable? Yes, the answer would be a 2 by 3. The same story here. It would be a 2 by 3 matrix, and when I add them, it becomes a 2 by 3 matrix. This is actually indeed a 2 by 3 matrix. But let us see how this will work. So I will start from number 4. Let me start from the right hand side. So right hand side, if I want to do it, I have to decompose this to rows. Of course, the rows include only one term, and columns again one term, but I have to multiply each row by each column. So I hope that you agree with me. It's 1, 6, 7, 15, 18, 21. What I have written here is the first product, and then similarly for the second product, it becomes 16, 18, 20, 32, 36, and 40. And now if I add these two matrices, usual normal addition, I have done something wrong because the answer should be what I have done wrong. Okay, I made a mistake here. 1 times 5 is not 1, is 5. Okay, now if I add them, it becomes 21, 24, 27, 47, 54, and 61. So you see, from theoretical point of view, these are very important to know. Okay, so this is another way of doing matrix multiplication, even though I usually don't use this method, but theoretically it's important to know if necessary in the more advanced lessons. Okay, and there is also another nice way, nice thing, especially in more advanced texts. It's important to know if your goal is to multiply a matrix by a column matrix. Of course you can do it, or you can always do the usual way. What I'm telling, don't get confused. What you learn, there is only one matrix multiplication, but we are looking at different alternatives for different situations. Theoretically, sometimes they are important. So it means that if I want to multiply a matrix by a column matrix, of course I can act usually just normal multiplication, but there is an alternative way to do that. What is that? This tells you, take the first number, multiply it by the first column of A. And then do the same thing. Take the second number, multiply it by the second column of A, and when you are done, add all these together. What you get is another way to calculate this product. And if you want to multiply a row matrix from the left to your matrix, you can take the first number and multiply it by the first row, take the second number, multiply it by the second row, and then after you are done, add everything together. What you get is just the answer to this product. To convince you about that, at least with some examples, so here you see I have A, this is my A, I want to multiply it by this column matrix. Of course, I can write it and just do the multiplication, but it is extremely important to know that this product can be decomposed into this way. How? I will take the first one, multiply it by the first column. I will take the second one, multiply it by the second column, and do this calculation. Let us just patiently do that. What happens? It becomes 11, 33, and then it becomes 24 and 48. And if I add them, it becomes 35 and how much is that? Is 70, 81. Yes? Now let us just do it normally. If I ask you to multiply your matrix, which is 1, 2, 3, 4, by that column matrix 11, 12, normally what you do, you take this one and multiply it here, so it becomes 11 plus 24, it becomes 35. And then you multiply this row by that column. 3 times this is 33 plus 48, and you see that you get again 81. Okay, so don't get confused about these many ways of multiplying these. These are theoretically important. Especially for your course, I think it is good to know this, the first three one. The first three one are, we will give you some examples of this type. Any questions so far? Okay, so let us go to the next topic. This coming lesson is extremely simple but extremely important. Matrix algebra against a number algebra. So we want to see, this is extremely important to pay attention to these differences. Okay, I want to summarize them in one place so that you already know what's happening. So let us understand the differences. So one difference you already know. If I have A and B numbers, A, B, B and BA are always defined. I can always multiply two numbers regardless of the order. And the answers are the same. But you remember, for matrix multiplication, sometimes AB is defined, BA is not defined, sometimes not neither of them is defined. And even in the cases that they are defined, there is no guarantee that they be equal. Okay? So this tells me that matrix multiplication is not commutative. So we talked about this. But when I say it is not commutative, it means that there exists a counterexample. It doesn't necessarily mean that you cannot come up with matrices so that AB is equal to BA. No, we can. For example, I have given you an example here. I have given you A to be this and B to be this. Let us calculate AB here. Okay, so AB is 1, 2, 3, 4 multiplied by 4, 2, 3, 7. Let me just confirm that. If I multiply this by that, it becomes 4 plus 6, which is 10. The next one becomes 2 plus 14, which is 16. The next one becomes 12 plus 12, which is 24. And the next one becomes 6 plus 28, which is 34. So you hopefully confirm that AB is the matrix that I have written here. But let me calculate BA. BA is the other way around. But this time what I have to do, I have to take this row and multiply it by this column. So it becomes 4 plus 6. Again, the answer is 10. The next one, 4 times 2 is 8, plus 2 times 4 is 8. If I add them, it becomes 16. You can convince yourself from the other two. So you see that I have two matrices. The entries are designed in a way that if you multiply AB or BA, the answer here becomes the same. The point is that if A and B are given matrices, you are not allowed to presuppose that AB is equal to BA. That is important. You can write AB is equal to BA only if in the problem that you are investigating, it is given directly as an extra piece of information regarding these matrices, or you yourself can demonstrate it indirectly from the information given in the problem at hand. Yes? So be careful about that. And this is the motivation of this definition. Commuting matrices. Two matrices A and B are said to be commuting if, of course, AB is equal to BA. And these commuting matrices are an important category of matrices. So whenever it's important to have this information in your mind if you want to work with matrices. Okay, so one very clear idea is that diagonal matrices of the same order commute. So one important class of commuting matrices are diagonal matrices of the same order. Yes, and the reason was clear. Yes, do you remember here? We had this formula for multiplying two diagonal matrices. This would be the product. But you know that there is no difference between A1 B1 and B1 A1 because these are numbers. So if I multiply them in the different order, I will get the diagonal B1 A1 up to Bn An. But this is exactly the same thing because each one of these products is equal to the previous product. So remember, one important class of commuting matrices are diagonal matrices. So this is why diagonal matrices are very extremely important in the theory of matrices. Okay, so for example, just give you a simple example. Consider the following matrices. Determine A and B such that A and B commute. Okay, so this is extremely simple. So it means that AB should be equal to BA. So then this means that multiply A from the left to B and equate it to the product in which B comes first and A comes second. And then what you do, you calculate the left hand side, just the normal product. So this becomes 2 plus 2A. 2A. The next one becomes 3 plus 2B. The next one becomes minus 4 plus A, and then minus 6 plus B. Yes, I'm just doing this quickly because I'm sure that you know what to do. And now I multiply this by that, so this becomes 2 minus 6 is minus 4. 4 plus it's 7, and then A minus 2B, and then 2A plus B. Yes? So this means that these two matrices should be equal if I am demanding this equality. There is no guarantee that this can happen. So this means that 2 plus 2A should be minus 4, 3 plus 2B should be 7. It's extremely important to write all of them. A minus 2B should be minus 4 plus A, and then 2A. So let me organize, keep the order. So minus 4 plus A should be A minus 2B, and then minus 6 plus B should be A 2A plus B. Okay, so the first two is enough to give me the answers, but you shouldn't be in a hurry. The first one gives me A equals to minus 1, B equals to 2. But it is extremely important to check the other two equations, because if one of them at least does not work, it means that it is not possible to fine-tune these A and B so that they commute. And the answer would be that these two matrices never commute. So it is extremely important to check these things are true. Let us check. If I put here, yes?
Shouldn't A be minus 3?
Okay, thank you very much. Yes, thank you. Should be minus 3. Is the other one correct? Yes. So now let us check this one. So if I put minus 3 here, it's minus 7. If I put these two numbers here, that's also minus 7, so that is also correct. But this becomes minus 9. So if I remember, this should work here, but so is it working or not? I don't see it's working. So let me multiply this once more. So this one by that is 2 plus 2a is correct, 3 plus 2b is correct, minus 4 plus a is correct, minus 6 plus b, that's also correct. Here 2 minus 3 minus 6, that's correct. 4 plus 7, a minus 2b, 2a plus b. Yes, everything seems right. And then this one should be equal to that one. This one should be equal to that one. This one should be equal to this one. And minus 6. Okay, so let us see if it works or not. From here, as you said, I should write a is equal to minus 3, b should be equal to 2, but here b is minus 2, so this is correct. And here, yeah, that's also correct. I don't know. So everything seems right, and this is my answer. Now everything was correct. So it means that if you choose a to be 2 and a to be minus 3 and b to be 2, these two are different matrices, but still they commute. Okay, any questions? Okay, another very important difference. Here I have given you a simple calculation. I have given you two matrices. Even there is no single zero in these matrices, but interestingly the product is 0. So let us double check. A times b, it's 1, 2, 2, 4 multiplied by 4 minus 6 minus 2 and 3. So this becomes, the first one is 4 plus minus 4 is 0. The second one, minus 6 plus 6 is 0. The third one multiplied here, 2 times 4, 8, 4 times minus 2 minus 8, again 0, and this is 0. Okay, before seeing what is coming, what is the difference here? Is this something you expect in numbers? Pardon? No, in numbers this cannot happen. That's called zero product rule, yes? In numbers, if I have two numbers multiplied together and that is the zero number, at least one of them has to be equal to the zero number. Or, yes? So this means we call it zero product rule. So this tells you that don't expect that the zero product rule works for matrices. Here, I have two matrices, none of them is equal to 0, but the product is the 0 matrix. Okay? So that is the second main difference between algebra of numbers and algebra of matrices. You need to pay attention to these details. Okay, so that is exactly what I have written in this remark. Another difference is coming from here. So there are three main differences. You lose commutativity, you lose the zero product rule, and you lose this property which is multiplicative cancellation. Okay? Multiplicative cancellation will work, we will see if we have time later when it works. But at least here I want to convince you that you are not allowed to think that I can cancel a from both sides. First of all, let us confirm that these two are indeed the same for these particular matrices that I have engineered to work actually. So here, A times B is what? 1, 2, 2, 4 multiplied by 2, 1, 3, 2. The answer is 2 plus 6 is 8, 1 plus 4 is 5, 4 plus 12 is 16, and 2 plus 8 is 10. And then let me multiply A by C. A by C is 1, 2, 2, 4 multiplied by minus 2, 7, 5, and minus 1. So what happens now? It becomes minus 2 plus 10 is 8. And then 7 minus 2 is 5. Minus 4 plus 20 is 16. 14 minus 4 is 10. So you see that AB is equal to AC, but B is not equal to C. So this means that if you see that AB is equal to AC, you know that in numbers, if A times B is equal to A times C, and if I guarantee that this number is not 0, then you are on the safe side. There is no other possibilities. B has to be equal to C. But this is not working for matrices. If I have a product like AB is equal to AC, even if the matrix A is not the zero matrix, you see this matrix even doesn't include 1, 0, and 3, let alone to be the zero matrix itself. But still, if you naively cancel this and conclude this B is equal to C, that is completely false, because you see that B and C doesn't even share one corresponding entry to be equal. So that is also an extremely important difference. So far I have explained everything for you. Then I am writing here, however, we see later that if the matrix A is invertible, the property that we will study later if we have time, of course, with you, then multiplicative cancellation is valid. Okay, but I have given you to get a taste of this situation, check the example below. So what I'm saying is that in some cases, you can have this cancellation, and that is what a property called invertibility. Okay, but to get a flavor of that, let me just do this example for you. So let A be this matrix, and let B and C be square matrices, each of order 2, so that AB is equal to AC. Show that in this particular case you can do this cancellation, okay, and conclude B is equal to C. If we have time later, we will learn that a property of this matrix is called determinant. Determinant of this matrix turns out to be non-zero, and then we will learn if that number that you can calculate from your matrix and is called a determinant is not zero, the matrix is invertible, and when it is invertible I am on the safe side to cancel this out. And calculating this determinant is just multiplying 1 by 4, multiplying these two, and then subtract them. It becomes -2, and this is very easy. So just if you give me this, if you know enough knowledge about matrix theory, just by looking at this, it's a matter of seconds to calculate its determinant and see that this is not zero. And there is a theorem, a little bit more advanced theorem, that if determinant is not zero, my matrix has this property which is called invertibility, and we show that if matrix A is invertible, cancellation is valid. But here you don't need to have that extensive knowledge to solve this problem. You will be able to solve it. How? For example, I would say that I want to show that if this product is equal to this product for arbitrary matrices B and C, then I can conclude. Okay, I would say let B be any matrix, I don't know, A, B, C, D, and C be, for example, E, F, G, H. Okay. We assume that AB is equal to AC, and we show that B is equal to C. Okay, so how can we do that? Okay, so let me calculate AB. AB is 1, 2, 3, and 4 multiplied by B. A, B, C, and D. Of course, you shouldn't expect to get numbers because B is an arbitrary matrix. So then it becomes A plus 2C, B plus 2D, 3A plus 4C, and 3B plus 4D. Okay? And let me calculate AC as well. So 1, 2, 3, 4, I multiplied by A, B, C, D, E, F, G, H. If I calculate this, it becomes E plus 2G, F plus 2H, 3E plus 4G, and 3F plus 4H. But now you are telling me AB is equal to AC. So this matrix should be equal to this matrix. So equality of these two matrices implies 4 equations. A plus 2C should be E plus 2G, B plus 2D, b plus 2d should be f plus 2h, and then 3a plus 4c should be 3e plus 4g, and 3b plus 4d should be equal to 3f plus 4h. Yes? Now, is there any way to work on this system to guarantee that this is equal to this? Let us see. What can I do? For example, okay, so for example, here I can multiply the first one by -3 and add it side by side to this. So let us see what happens. If I multiply the first one by -3, it becomes -3a minus 6c minus 3e minus 6g. And then let me write the third equation exactly below that. And then add them side by side. What happens? This one and that one are gone. I get minus 2c. This one and that one are gone. I get minus 2g. And if I divide by 2, minus 2, I get this one. So c is equal to g. Agree with me? Now when you say c is equal to g, it means that this term and that term are the same, because c and g are the same, so I can cancel them from both sides. Then it gives rise that a is also equal to e. Okay, so this implies that a is also equal to e. Okay, and then come here now. This doesn't give you any new information. Okay, so now you need to play the same trick. So you need to multiply this by -3 and add it to the last one. Okay, so let me just do that one here. If I multiply the second one by -3, it becomes this. And then let me write the fourth one exactly below it. And then again I add them side by side. This is gone, I get minus 2d is equal, this one and that one are gone, minus 2h, and then again I get that d is equal to h. Now that d is equal to h, I go, for example, here, 2h is also equal to 2d, and then it gives me that b is equal to f. Okay, I hope that this is enough. Yes, is it? To show that these two matrices are equal, I need to show that A is equal to E. Yes, it is in my list. I need to show that B is equal to F. Yes, it is here. I need to show that C is equal to G. It's here. And I need to show that D is equal to H. It's here. So then this means that, yes, in this case, matrix B is equal to matrix C. But this is something that this is not guaranteed all the time. Is that understandable? It's just a simple algebra. Any questions? Okay, so as the summary, let us review this again because this is extremely important. The product of every pair of real numbers is always defined. Whereas this is not the case for matrices. As we learned, for A times B to be defined, the number of columns of A has to be equal to the number of rows of B. So this is one difference between algebra of numbers and algebra of matrices. Second item, in multiplying two real numbers, the order that we multiply these numbers is irrelevant. But we have to pay close attention to the order we multiply matrices. Depending on the order we multiply two or more matrices, the final answer might be totally different. This is the second item. Do you remember the third? Matrix multiplication does not obey the zero product rule. So if you get this is zero, don't get immediately this conclusion that either the first matrix should be zero or the second matrix should be zero. The multiplicative cancellation in general is not valid in matrix algebra. So this is extremely important to pay close attention to these differences. Okay. So far we have talked about the differences, but there are also some similarities. Yes. So similarities are, this is something very easy to understand. If you take a matrix and multiply it by the zero matrix, exactly like you multiply a number by a zero number, definitely the answer becomes zero. So this is somehow is inherited by the matrices. But of course in matrices you need to pay attention to the order of multiplication. If you have a rectangular matrix A, m by n, if you multiply it by a zero matrix from the right, which has the same number of rows as the columns of A, then the answer would be the zero matrix. But the zero matrix that is produced is not this zero matrix, because the order of the product should be m by p. So it's important to pay close attention to it. But you say that if matrix A and matrix 0 are multiplicative, if you can multiply them in any order that you can multiply them, the answer is the zero matrix. And of course, you need to also fine-tune the order of the zero matrix in the product. But of course, in the case that your A is a square matrix, then it doesn't matter if you multiply A from the left or you by the zero matrix, or that zero matrix by A from the left, you get the answer equal to 0. So this is also another class of matrices that you need to remember. They commute. The square zero matrix commutes with every square matrix of the same order. And I have given you some examples. Of course you can, it is so important, the proof is so important that I just want to ignore that. But if you multiply these two matrices, actually you don't need to multiply at all, because you see that you have a zero matrix, and then this is definitely a zero matrix. But this matrix is 3 by 2, this matrix is 2 by 4, so you know that you have to produce a 3 by 4 matrix, but it is the zero matrix. So immediately I write 3 by 4 matrices. And again here you have a zero matrix multiplied by a matrix. The answer definitely would be a zero matrix, but you need to fine-tune the order. This is 3 by 1, this is 1 by 3, so the order would be 3 by 3. But if you have a square matrix, it doesn't matter if you multiply it from the left or you multiply it from the right, it becomes exactly the same zero matrix. It's very simple. Now this one I want to talk a little bit more. This is also another similarity between matrix algebra and number algebra. In numbers I can multiply any number by 1 and the answer is the number itself. It's more or less the same with matrix theory if I give the role of 1 to the identity matrix. Okay? But there is a difference here. Zero matrices can be rectangular matrices, but identity matrices by definition have to be square matrices. But in any case, if the product is defined, this product gives you the same matrix back. If I have this matrix, I want to multiply it by a in means it is n by n, so I can only multiply it from the left because the n's should match. And then the answer would be the same matrix. So it means that if you can multiply the identity matrix in any order, if it is possible to multiply, don't worry about that. The answer becomes the same matrix. And of course, if the matrix is the square matrix, it doesn't matter in which direction you multiply it, the answer becomes. This is also another class of commuting matrices. So the zero matrix commutes if it is multiplicable. The identity matrix also commutes with every matrices. So this is important to know. But let me prove this. It was very trivial here because whatever you have is 0, so it means that if you multiply, everything becomes 0. Even if you add, then finally it becomes 0. It is less trivial here. Let us show this case. For example, let me concentrate and show this one. So here I want to show that A with this property, with m rows, n columns, multiply that, it becomes this one. Hopefully you know that from order point of view everything matches, yes, because this is n by n and this one and that one are cancelled, so this is n by n. Okay, so what I want to do, I want to concentrate on the ijth entry of this matrix. So I would say that let I be an integer between 1 and m and j be an integer between 1 and n. We show that ai number ij is equal to a number ij. If I can show this, I am done. It means that every entry of this product is equal to the entry of the right hand side. But this you know what to do, yes? You can write it as a sigma, and then you choose a counter for your sigma, goes from 1 to n in this case, and then you write the first matrix, which starts with an I, ends with k. I matrix starts with k, ends with j. Okay? But do you remember I told you that you can write this as the Kronecker delta? Do you remember? The I matrix is 1, the entry in this is 1 if k and j is equal to 1, and this is 0 if this is not the same. And that is exactly the definition of Kronecker delta. So this means that I can continue and write it as sigma k goes from 1 to n, a I k delta k j. But do you remember I told you that if you have a Kronecker delta under the summation notation, this Kronecker delta kills this summation but changes k to j everywhere. So it becomes a I, instead of k I put j, and that is exactly the right hand side. So you see that this is now on the safe side. If you can multiply a matrix by the identity matrix, the answer is always equal to the identity matrix. Okay, I prefer to stop here. There are more similarities. Okay, let me just also write this. So this is an example. If I multiply this is an identity matrix. Is it possible to multiply? Yes, because I have 3 rows and 2 columns, and this is 2 by 2. It's possible. So if it is possible, don't think. The answer is the matrix itself. Here, this is identity matrix 3 by 3. Is it possible to multiply? This is 3 by 3. This is 3 by 2. It is possible, so don't think. The answer is the matrix itself. And in this case, both of them are 2 by 2, so in both directions it works. So in each case, the answer is the matrix itself, and you don't need to calculate anything more. I just mentioned the theorems, but I will not discuss about that. We come to this later. That was a lot of information. So I talked about the differences between matrix algebra and number algebra. Now I am talking a little bit about similarities. We learned about multiplying a matrix by the zero matrix, multiplying a matrix by the identity matrix, and then we learned some theorems that I will discuss about them later. So here this is a theorem. This is very similar to this. That if I want to multiply two numbers by a number, I can just float this number around, it doesn't matter. But of course it is not associativity, because associativity means that these things should be of the same type. But here, alpha is a number, A and B are matrices. And then very interesting property, even though we lost commutativity, but distributivity and associativity remains for us. Otherwise, it would be very hard to work with matrices, because then there are no properties left for us. And then later we will learn that we can distribute a matrix to a sum or a difference. But of course, because matrix multiplication is not commutative, you need to pay close attention in the direction that you are distributing. I will come to this later. And then fortunately we will see that associativity is also left for us. So we only lose actually commutativity, the zero product rule, and the cancellation law in general. But any other things that we were able to do with numbers, it seems that we have them still with us. Okay, so that would be the topic of the next lesson. So I will stop here. Any questions? Okay, so let me just stop at the 5. Yeah.
Oh, yeah, this one. Last one.
Yes?
Last theorem. If you just scroll down to the last theorem.
Here?
No. The side we were on, but it wasn't quite showing the whole page.
I don't understand. This is the last theorem I proved for you.
No. There's a side after this one. Yeah.
This is after this.
And then the last one. This page. Yeah. The distributive. Yeah. I just wanted to see if I wrote it down.
Yeah. I will talk about this next time, of course. But if you want, you can have it. Yes.